Hello YouTube, this is Tutor for Hire back again with another video. This is going to be the fourth video of the calculus series, and I'm just so excited to be with you guys today to talk about it. The title of this video is Velocity versus Distance, Slope versus Area, because today we're going to be talking about how the slope and area with respect to the slope of a tangent line and distance and the original functions, how they all relate to each other. So I'm really excited, and so let's get into it. As you can see, I have a new application which is much better than typing it out on Word. I think this will help you guys a lot in your understanding and things like that. So just hang back and just absorb everything you can within this video today. So as you can see on the left hand side, there's a distance formula, and on the right hand side there's a velocity. Now, as we talked about before, velocity is the first derivative or the rate of change or the slope. Actually, you know what, let's talk about that right now. So when a function is linear, meaning it is a straight line, or it could fit into something that looks like this. Oh shoot, sorry about that. Oh man, that's not good. That is not good. Let's go here maybe. You know what, let's just go with it. Y equals mx plus b. When it fits into something like this, or it's just the graph is a straight line, there's no breaks in it, there's no shifts in it, it's a linear function. What that means is that the slope is constant. When the slope of a graph is constant, that means that its rate of change is consistent from point negative infinity to positive infinity. It'll always be the same no matter what you put in there. The graph will constantly be expanding at the same rate for all eternity, right? So if you're looking at a distance formula, and this is a linear function, so if you're looking at a distance formula, the slope of this function will be the first derivative. It'll be the rate of change. It will be when we graph out the slope of this, it's going to be the velocity function. They're the same thing. But calculus isn't about taking a linear function and graphing the slope, because that's like algebra or something like that. Calculus is about taking the looking at a nonlinear function, something like this, where it's nonlinear, up and down, it's crazy. And what we do is, because the slope is not constant on this line, it's constantly shifting, you take an ordered pair, say here, and then you graph a tangent line like this, and because this tangent line is constant, you're able to take its slope. And so you do that by taking the first derivative, and the first of the nonlinear function, and the first derivative of the nonlinear function is also known as the slope to a tangent line, and it shifts based on what point you take in the graph. So at some points the graph will be positive, and it'll have a positive it'll be positive, and then at some graphs, in some areas it'll be negative, and at some areas it'll be undefined, and at some areas it'll be there are all sorts of ways that this plays itself out. But basically what calculus is trying to find the graph, trying to find what areas it's increasing and decreasing and things like that for a nonlinear function. The linear functions are easy enough. So basically, yeah, so this is going back to what we were talking about. This is a distance function, And as we said before, the original function could be measuring distance, it could be measuring the height of the graph, it can be measuring whatever you want. And the first derivative will be, for distance, it'll be velocity. For the height of the graph, it'll be growth rate. All these names are interchangeable, and they all involve the same processes, which is finding the slope or the slope of the tangent line or the rate of change or any of these things you want to say. They're all kind of the same thing in a way. But so this is a distance formula, and as you can see, it goes down to negative infinity and goes up to positive infinity, and it has a constant growth rate, and it just depends. And the function here is f of x is equal to v multiplied by x, with x being a constant. A constant just is 1, 2, 3, 4, a million. It's any constant number, and this will be going up or down depending on how big the constant is, but the rate of change will be the same. It just depends on, the graph will just depend on how big v is. So if v is 6, it'll be here, and if it's 0.1, it'll be down here, whatever the case may be. And the first derivative, as we talked about before, is basically the slope, right? So it'll be in this particular instance, if you take the first derivative of this function, which is f of x is equal to v multiplied by x, or you could take the slope-intercept form, y equals mx plus p, m is equal to the slope. In this case, it'll be the constant v. But if we're taking the first derivative, as we talked about with the rules, the first derivative of any function that has a constant multiplied by an isolated variable like x with no exponents or anything like that, it's just by itself, just an isolated x multiplied by a constant, what you're going to get is, so we'll say dy over dx is going to be the constant multiplied by the first derivative of the isolated variable. The first derivative or the rate of change for any isolated variable, as we talked about before, is always going to be 1. If it has no exponents or anything, it'll always just be 1. So it'll be 1 multiplied by v, which is equal to v. And this is the graph for the velocity function. It's just v, which is a constant number, which as we know, if it's just a constant number, it'll always be on the y-axis, it won't be on the x, and it'll just be a straight line. So we'll say this is v. We don't know what v is, but we're just saying it for right now. This is v. Okay? It's a straight line. And now we're going to talk about, let's say we were just given this graph. We say your teacher gives you this graph, says this is a velocity function. Find the original distance function that gave this velocity function. Find the distance function which shows us that this is the first derivative, or whatever the case may be. How can we get the distance function from the graph of the first derivative, right? Well, here's the rule. The area underneath the slope of the first derivative, so on this graph, the area underneath this line, this area, is equal to the function that gave us the first derivative, or in this case, this area underneath the line would be equal to the distance function. And what is this area, right? It's a rectangle. It's not a square, it's a rectangle. What is the area of a rectangle? The area of a rectangle is equal to length times width, right? Or height times width. Height times width. So in this circumstance, the height would be v and the width would be x, because it goes on to infinity. We don't know how far it goes. So the area of this rectangle, or the area underneath the slope in the velocity function, would be v multiplied by x, right? Because it's a rectangle, so the area would be the height multiplied by the width, which would be vx. And what does that look like, right? Vx. So they're the same. So the area under the slope of the first derivative, or under the graph, or whatever you want to call it, in the first derivative is equal to the distance function. And that's how it relates to the that's how you can find the function that gave you through the graph of the rate of change or the slope. You can find, if you just have the graph of the slope or the rate of change, you will be able to find the function that gave that rate of change graph. So long as you know the area and all that stuff. But anyway, that's a pretty cool thing. It's how it all relates. And I know my handwriting isn't very good, but I just think that's very, very cool how they do that. So moving on to the next phase of the lesson, we're going to talk about if we're looking at, let's graph another thing. So we're going to go here, and let me just start off by saying, when we were talking earlier about graphs and how sometimes the slope in a nonlinear function can be positive and sometimes it could be negative, and how those, and sometimes at some points graph can be discontinuous. Let's look at something like that. So we're going to have this is going to be a velocity function. This will be positive velocity. This will be negative velocity. So, and this will be t over time. So as the man, let's say he's in an automobile. As the man goes forward, he'll be above the graph, and as he goes backwards, he'll be beneath the graph. And let's say it goes something like this. And we'll say this is 6, and we'll say this is 3, right? And we'll say the areas of these little boxes are the same. So it'll be 3v, and then the area will be negative 3v. So he's going, and so like I said, when the slope's going downwards, it's going to be a negative function. So what does this mean? So he's going backwards on the negative velocity, right? So underneath this line, for 3 paces, he's going backwards. Above the line, he starts out and he goes 3 paces forward. So his total distance, you could say, is 0, but that relates to the original function. But if we're just looking at the areas of these boxes, because one is positive 3v and one is negative 3v, the total area will be, of the graph will be, 0, because they cancel each other out. But let's look at this real quick. So I don't know if you guys can understand this as well, but basically it's a man in a car. He drives forward 3 feet, then he goes backwards 3 feet. So he ends up at the same place over a course of time. So if we're looking at the conditions of this function, it would be something like v of t. This is just the function. It'll just be v of t when, or you know what? Let's think about this. Let's talk about when is the function positive and when is the function negative. So it'll be positive v when t is greater than 0, because you see it starts after 0. When t is greater than 0, the function starts after 0, and less than 3, right? Because he stops at 3, he stops going forward at 3, and he starts going backwards at at 3, right? So what does that mean? Because the needle jumps here, because it goes from he keeps going positive until it's, as soon as he hits 3, it's like there's like a shift. He goes from positive to negative. What does that mean? That means t is undefined at 3, right? When t equals 3. What does that mean? That means that this function is discontinuous. You have a positive slope and you have a negative slope, and they're not connected because at 3 the function is undefined. You can't be going forward and backward at the same time at 3. That's just illogical. So at 3 it's undefined. And because it's undefined at 3 and both functions are not touching each other, both slopes are not touching each other, this function is discontinuous. And let's look at when is it negative. So it'll be negative v, negative velocity, when, and you guys probably can already see this, 3 is less than t, which is less than 6. And as you can see, the graphs end at 6, so he's not moving at 6, and he's not really moving at 0. The only times he's moving is between 3 and 6 and 0 and 3. He's not moving at 0, and he's not moving at 3, and he's not moving at 6. He's going, you see it's going like up at 6, but he's not really moving forward at 6. So it can't be 6. So it's not less than or equal to 6. It's just, it can't be 6, it can't be 3, and it can't be 0. So it'll be negative velocity between 3 and 6, positive velocity between 0 and 3, and then it'll be undefined at 3, and it's a discontinuous function. Now if we're looking for the distance formula, we can kind of actually do it logically if we're looking at this. So the man is going forward and backward for the same amount of time at the same speed. That means, as we talked about it before, the total distance would be 0 because he would drive forward then drive back, which means he would end up at the same spot. So it would be something like, if we had to look at this, it would be something like the function would be, he would just be driving at the normal rate if this defines the original distance function, and it would be something like this: via t if 0 is less than or equal to t is the time, which is less than or equal to 3. And because he's just that's just the normal function for him going forward. That's the normal function for what he's doing at that moment. T is time, so you put in 3 time, you put it in the function, he's driving forward. And it can't equal 3 because he is still technically going at 3. He's just at that distance. But it'll be, and then for past 3 it'll be v6 minus t. And the reason we have to make it look like this is because these two functions have to agree with each other. Just like these three have to agree with each other. You can never have two contradictory functions, right? So this function 6 minus t ensures that he's going backwards after a certain period of time. So for the distance at 3, so let's put 3 less than or equal to t less than or equal to 6. So let's put in 6 here, right? 6 minus 6 is 0, velocity equals 0, right? His total distance once he reaches 6 is 0, as we described, because he goes forward, then he goes backwards 3, both times. So he'll end up at 0 after 6 seconds, right? So if you put in 6 into this function, you'll get 0 distance, which is true because he goes forward and backward, right? If you put in 3, and 3 is up here and 3 is down here, if you put in 3, you'll get 6 minus 3, which is 3, v of 3. And if you put in 3 here, you'll get v of 3. And they're equivalent at 3, so they agree with each other. They don't contradict each other. And you might be thinking, well, why is he not able to do it with this function? Hey guys, sorry about that. I just had to make a quick couple of changes, but I wanted to pick up where we left off in the last, where I just picked off, where I had to restart a little bit. Basically, the question was, why is it that the velocity function, why is it undefined at 3? And why can the velocity function not touch 3? Whereas the distance function can touch 3. Why are these symbols different for both functions, even though the functions are so related? Well, you got to think about what the distance function is measuring. The distance function is measuring distance, and you plug in a time, and it gives you the distance. So the man, as we discussed, he goes forward 3 spaces, then he goes backwards 3 spaces. So the total distance is 0. He ends up where he starts, but he does that over the course of 6 seconds. So t, if you plug in 3 in terms of the time, we have his exact location. It's at the end of 3. It's at the end of him going forward, and it's at the beginning of him going backwards, right? So if we plug in 3 into the function, we get, where is he at? He's at, if we plug in 3 seconds for t, he's at the value of 3. And if we plug in 4 seconds, so he would be at the value of he would go forward 3, then he would go backwards 1, so he would be basically at the value of 2, because he would be 2 spaces away from where he originally started. That would be his total distance, would be 2. So at any given time, we can find out where he's at in terms of distance. We know where he's at. So t can equal 3 because he would be at 0. It can't equal 6 because he would be at 0. It can't equal 3 because he would be at 3. It can't equal 4 because he'd be at 2. And it can't equal 2 because he'd be at 2. So we always know where he's at in terms of distance with respect to time. So he can equal these values. And so we can do this logically, but as in terms of velocity, and just remember, at the end of the day, these are all functions. The distance function is a function that's a set of ordered pairs. It has a set of inputs and outputs, and so is the velocity function. And in the velocity function, t equals 3 is outside of the function's domain. It's not defined there, but let's think about it rationally. So he's going forward at for a specific time at a specific speed, and then he's going backwards at a specific speed at a specific time. And these speeds are different, right? And at a point, you can sort of think of this as a point of transition, but it's not defined. So you can't be going forward at a specific speed and backwards at a specific speed at the same time. That's just illogical. So this point, you can think of it kind of as a point of transition, but it's undefined. It's outside of the domain of the velocities function. So if we had a real velocity function here, you'd be able to see that if you plugged in 3 to a calculator, it would be undefined there. Maybe it would be divisible by 0, or maybe it would be a function where divisible by a negative number or something like that. It would basically, if you were to plug in 3, it would be a undefined term. It's just not defined here. So yeah, it's outside of the function's domain. So the needle here jumps. It's not it's at such a curve that you can't say that it's continuous. or yeah, it's continuous, it's undefined at t equals 3. And so for that reason, because you can't touch, it's also it also 0 is outside of its domain, outside of the function's domain, and 3 is out, or 6 is outside of the function's domain. So if you put any of those numbers into the function, you're going to get undefined, because if you remember the function, I sort of deleted it, but it wasn't touching 6, it wasn't touching 3, and it wasn't touching 0. They were not, um, the only thing that defined the velocity was the space between those numbers. Yeah, velocity, it's defined by how it's moving, not necessarily when it's just at a point of dislocation. So but anyway, that's all I really wanted to talk about with this video. Thank you guys for watching, and stay in touch, and we'll keep it up in the next one. Thank you.